Now we will discuss functions. Given two sets, D and C, where I will refer to D as the domain and C as the codomain, a function from the domain to the codomain is just a subset of the Cartesian product of the domain with the codomain that has the following property. For every element in the domain, there exists a unique element in the codomain such that x comma y is an ordered pair in this subset. And for clarity, I will usually refer to the subset as the graph of the function. So in other words, for every x, there's a unique output y such that x comma y is a point on the graph of the function. And usually this point, the y-coordinate, the second coordinate, is usually denoted f of x, just like it is in college algebra. And so from a computer science perspective, the approach I usually think of is that the function is a black box that takes some element x in and pops out some unique element out. Of course, abstract definition aside, we've all seen functions before in previous courses. For instance, an obvious example is to take the function from the real numbers to the real numbers given by f of x equals x squared. So here it's worth noting that the domain and the codomain can be the same set. And so, of course, this is the formula for the function that we're used to. It's worth pointing out that if we're following the textbook definition, really the function is being identified with the set of ordered pairs that form x comma x squared. We're identifying the function with its graph. As an example of something from a previous course that's not a function, you can consider g from the natural numbers to r, given by g of x equals plus or minus the square root of x. And the reason why this is not a function is because we see that g of 1 is either 1 or negative 1. In particular, that means that the ordered pair 1 comma 1 and 1 comma negative 1 are both in the graph of this function. And we see that's a violation of the definition of function because for every x, in this case 1, there's supposed to be a unique y. There's supposed to be a unique second coordinate, and here we have two possible second coordinates. And so this is not a function. In some branches of mathematics, this might be called a multi-valued function. As another example, we can consider the function from the real numbers to the real numbers that's given by the natural log of x. So, the problem with this example is that we don't know the value of the natural log of negative 1. It does not exist as a real number anyhow. And so we run into a problem because that means that in the graph of this function, there is no ordered pair where the first coordinate is x. And the definition of a function says for every x, in this case negative 1, there needs to be unique y such that you have an ordered pair x comma y, and here we don't have that. We have no y coordinate, and here we have too many y coordinates for that given fixed x coordinate. The idea is that for every element in the domain, there's a preferred element in the codomain. Now we will talk about image. And so first off, notice on this slide I finally actually defined that whenever I talk about domain of the function, it is the first set. And codomain is always the second set. So the domain is the set of first coordinates, and the codomain is, well, contains the second coordinates, possibly more things as we will see below. And so the image of a function is defined by taking any subset of the domain and looking at the set of possible y-coordinates, the outputs of that function, when you only restrict your attention to those particular inputs. And this is where we get a concept familiar from other math courses. The range of a function is just the image, also sometimes called the image, is just f of the entire domain. And so as a concrete example, let's consider the function below, where the domain is the letters A through D, and the codomain is the numbers 1 through 3, and the function sends A and B to 1. So in particular, if I were to actually look at the graph as an ordered collection of ordered pairs, the actual set would have A comma 1, B comma 1, C comma 3, and D comma 3. And so this is a function. It's a set of ordered pairs where all the first coordinates are from the domain and all the second coordinates are from the codomain. And for every first coordinate, there's a unique second coordinate. For every element of the domain, it appears exactly once in this set of ordered pairs as a first coordinate. So let's actually look at the image. So let's take A and C, and let's take the image of A and C, and we see that we get 1, because f of A goes to 1, and 3, because f of C goes to 3. And so that is the image of the set of blue vertices under this function. Likewise, we see that the range of the function is just 1 and 3. So it's important to note when discussing functions that the reason why we call this a codomain instead of a range is because the codomain can be bigger than the range. Just like it is in previous math courses, we always ask what's the range of a function. It's because usually the codomain is all real numbers. On the other hand, in previous courses we do ask about domain, because actually what you study in previous courses should be called a partial function. Not every real number has an output. For instance, divide by 0 errors cause problems. But in more advanced math courses, we always specify the domain and the codomain in advance before we define a function. Now we ask ourselves, how many functions are there where the domain consists of the integers 1 through n and the codomain consists of the integers 1 through k? It turns out we actually do know how to solve this problem already, and so I will illustrate it with the case where n equals 3. So what does a typical function look like? And let's say k equals 2. What does a typical function look like in this case? Well, you have to specify what f of 1 is, you have to specify what f of 2 is, and you have to specify what f of 3 is. So let's say f of 1 was 1, f of 2 was 1, f of 3 is 2. But it turns out there's another way to look at this function, so it's worth pointing out that using the definition of function the book uses, we identify a function with its graph, and so that this is actually the set of ordered pairs. But in our particular case, because our domain consists of the positive integers, another way to denote this function is to just write it as a triple of numbers. So what do we put in the first slot? Well, we put what f of 1 is. In the second slot, f of 2, f of 3. In the third slot, and so in general we can do this. Given a function f, you can consider the sequence f of 1, f of 2, all the way up to f of n. And so for every such function, you get a sequence. Hold on, let me, real-time mistakes here. It's a sequence, order matters. And you can actually go backwards. Given such an n tuple of numbers, where each of the AIs is between 1 and k, you can get a function. You just define f of I to be AI. The f of I is just the ith coordinate. And so, at least in the case when the domain is the integers 1 through n, we see that the set of functions from n to k is essentially the same thing as a Cartesian product. Right? For each element in the domain, you have to pick one element in the codomain. That's essentially the same thing as picking the ith coordinate. And as we already know from the product principle, we already know how to solve this problem. We see that the number of functions from n to k is actually just k to the n. Right? Multiplying k by itself n different times. Now we will discuss composition of functions. So now we have to take two functions, one going from a to b, so a is the domain, b is the codomain, and another function going from a set b to a set c. So b is the domain here and c is the codomain. In particular, it's very important that the codomain of f is the domain of g. And when you're in that circumstance, you can define the composition of two functions. And its domain is the domain of the inner function, so a in this case, and its codomain is the codomain of the outer function, so c in this case. And you define the composition of the two functions exactly as you do in calculus and other courses. G of f of a is just g applied to f applied to a. And it's worth noting this is well defined because given any input element in a, f of a is an element of b, and so you can actually talk about g of f of a, which is in fact in the set C. So you do actually get a well-defined notion of composition of functions. As a good reminder of linear algebra, in linear algebra, instead of sets, one works with vector spaces. Instead of functions, one works with linear transformations, and then the composition of two linear transformations is also linear transformation. And one of the advantages of that approach, of course, is that function composition corresponds to matrix multiplication, so it's a little easier to work with. And so you've actually seen function composition at that level before, just now we're have to work with arbitrary sets, which is important for discrete mathematics because in our case the sets are usually finite sets and not vector spaces. As an example of composition of functions, let's let A be the set consisting of little a, little b, little c. Let B be the set consisting of little x, little y, little z. Let C be consisting of the numbers 1 and 2. Let's look at f to be defined as this function. Here I am actually writing it down explicitly in terms of ordered pairs. So f sends a to x, b to y, and c to x. We do see that this is a function because for every element in the domain, there's a unique ordered pair with that element as its first coordinate. Similarly, we've got the function g here, and I leave it to you to check that g is also a function. And so now we ask what g composed with f is. And we see what we have to do is for every ordered pair in f, we take that first coordinate. So for example, a. And then we apply f to a, we get x. And then we apply g to that. And so now we look over here, and where do we find the x? We find it right here. And what's g of x? G of x is 1. So this corresponds to the fact that g composed of f of a, g of f of x, f of a, just g of x, which is 1. Similarly, f sends b to y, g sends y to 1, so g composed of f sends b to 1. And finally, f sends c to x, and g sends x to 1. And so we see that the composition is the function which sends all 3 points, a, b, and c, to the same element 1. And it's interesting to note that the range of G composed of F is just the subset consisting of 1 by itself, because the only way you could have gotten to 2 was through Z, and unfortunately Z is not in the image of F, and so that point never occurs. Finally, we will discuss some properties of composition. Most of these are straightforward and familiar from the study of vector spaces. If you've got 3 functions, one from A to B, one from B to C, one from C to D, we see that the domain and the codomain of the first function is the domain of the second. The codomain of the second is the domain of the third, and so we can actually do these 2 compositions: G composed of F composed with H, or F composed with G composed with H, and it turns out they're the exact same functions. Likewise, if you define the identity map to be the function that sends every point to itself, then if you compose with the identity maps, you don't do anything. And so this is familiar from linear algebra. If you compose 3 linear transformations, that corresponds to multiplying 3 matrices, and matrix multiplication is associative, and multiplying by the identity matrix doesn't do anything. So this is a similar type of result, but it's for abstract sets instead. And we aren't going to prove it, thankfully. And so that is it for this video.